All right, let's shift our conversation a little bit. Instead of talking about money, let's talk about rabbits. All right, so let's say we start with 100 rabbits that are growing continuously at a rate of 5% per year, let's say, if that's our unit of time. And we've got our variable t here, which is time. So we might be curious about looking at different times in the future and seeing how the population responds. And let's say we also are curious about looking at the situation where our population has doubled. We've gone from 100 rabbits to 200 rabbits, because remember, this is our final population size. And what if we wanted to solve for t? What if we wanted to figure out the amount of time that it would take the population of 100 rabbits to double to 200 rabbits? What would we do? So what's t? Okay, so I'm good at algebra. And I feel like a good start is to get rid of this 100 over on the right-hand side. So I'll divide both sides by 100. So we end up with 200 over 100, which is actually equal to 2. And that's equal to e to the 0.05 t. Okay, now what do I do? How do I deal with something that looks like this? How do I deal with an exponential? We haven't learned the algebra tools for this. All right, well, the answer comes in the form of logarithms. Logarithms are just functions that have been defined to be the inverses of these exponential functions. Okay, so logs are the inverses of exponentials, and a log with base b, like letter B in quotes, a log with base b will undo an exponential with base b. For example, what if we had an exponential, 10 to the x, and I want to undo 10 to the x. I want to get back to x. Well, this is exactly what the log does. A log of base 10, because our exponent is base 10, will give you x. Log base 10 of 10 to the x will give you x. All right. Similarly, if we had another number, y to the 72nd, we could make the statement that the log of base y of y to the 72 is equal to 72. That's what the log does. It undoes the exponential, and it pops out whatever was in the exponent. Now, it's important to realize that log base 10 and log base y are two different functions which are designed to be the inverses of two different types of exponentials. So, there's a little bit of an inefficiency that happens where you need to define a new function based on whatever type of exponential you're dealing with. And we'll learn more about how to simplify that process in the future. But for now, it's important to understand what the log does. It undoes the exponent. All right, and then the natural log. Okay, so the natural log undoes an exponential that looks like this, something where you have the constant e as the base of your exponent. And the natural log is just your log of base e. We just write it differently because it's super important. It's by far the most important log that's out there. So the natural log of e to the x will be the inverse function of your e exponential, and that will be what gets you back to x by operating on this exponential with the natural log. Okay, just as logs are the inverses of these exponentials, it turns out that exponentials are the inverses of these new log functions that we've defined. For example, let's say you had a log expression. So log base 10 of some value x. All right. Well, it turns out if I raised this whole term, if I raised the base 10 to this whole term, it effectively undoes the log. This is what would give me x. So I pick the exponential with the same base as the log. In other words, let's see, an exponent with base b will undo a log of base b, just as we've seen here. Or, for example, if I had, like the natural log of 72, I don't know why I'm so excited about the number 72 today, but the e raised to this whole power will spit back out 72. All right, so exponentials will undo the logs. Great. And then one last quick point is that regardless of what base you're using, the log of the value 1 will always be equal to 0. And the log of the value 0 will always be equal to negative infinity. And the reason for that is if you plotted logs, if you wanted to see what they looked like, if you plotted the function on the y-axis versus some variable x, they would always look sort of like this. They increase forever, but the rate of increase is always decreasing. And they always intersect the x-axis at x equals 1. All right, I think we'll end it there. And in the next video, we'll talk about some of the rules that we use for manipulating. Oh, no. Oh, yeah, I can't forget about this. Okay, so getting back to our question, how would we deal with something like this? Well, we know we can get rid of exponentials with the log function. So let's take the natural log of both sides. Here we end up with natural log of 2 is equal to the natural log of e to the 0.05 t. And here we end up with natural log of 2 is equal to 0.05 t. And then we could solve for t as the natural log of 2 divided by 0.05. Boom! We can solve for the half-life, sorry, not the half-life, the doubling time, the time it takes for the population to double. That's essentially what we've done here. We'll probably ask you lots of questions about things like that when we do some exercises in class time.